Under a shell of ice miles deep, on a moon no bigger than ours, hides an ocean with twice the water of every sea on Earth. Warm, salty, pitch black. For decades we called it our best hope for alien life. But this water may be sealed, poisoned, and starving. We will fall through cracked ice, cross a storm of killing radiation, and reach a sea that swallows all light. If wonders like this pull you in, like and subscribe. Prepare yourselves. We begin. 400 million miles from the Sun, a frozen moon circles the biggest planet in our solar system. It looks small, quiet, a pale marble streaked with red, spinning in the dark beside Jupiter. Scientists gave it a soft name, Europa, borrowed from an old Greek story. For most of history, nobody thought twice about it. Then everything changed. In the year 1610, Galileo Galilei pointed a crude telescope at Jupiter and saw 4 tiny points of light. Europa was one of them. He had no idea he was staring at a world that would one day become the most tempting target in the search for alien life. That took another 400 years to understand. Here is the promise that hooked us. Europa is about the size of our own moon, a little smaller. But underneath its icy crust, scientists believe there is an ocean of liquid salt water. A real ocean. Dark and deep and warm enough to stay liquid, and it may hold more than twice the water of every sea on Earth combined. Every wave, every trench, every drop in the Pacific and the Atlantic and the Arctic doubled, then hidden inside a moon you could cover with your thumb in the night sky. That single idea electrified scientists. On Earth, everywhere we find liquid water, we find life in the deepest trenches, inside boiling volcanic vents, frozen into Antarctic ice. Life clings on. So a giant, stable, salty ocean sitting quietly for billions of years sounds like the perfect cradle. A place where something could have stirred and grown and swum. For decades, that was the dream. Europa became the golden child. Books, missions, headlines. People imagined creatures drifting through its black water, glowing softly, alien and alive. Every few years a new study would land, and the excitement would spike again. This was the place. This was where we would finally learn that Earth was not alone. The deeper scientists looked, though, the stranger the picture became. Because a hidden ocean is only the beginning of the story. An ocean needs more than water to make life. It needs energy. It needs the right chemistry. It needs a way to keep that chemistry moving, mixing, feeding. And it needs to dodge a long list of quiet killers that can turn a promising sea into a sterile tomb. One by one, over the last few years, new discoveries have started chipping away at the dream. A measurement here, a calculation there, each one small on its own. Together they hint at something disturbing, that Europa's ocean may be one of the cruelest tricks in the entire solar system, a place that looks perfect from a distance and hides a terrible secret up close. This is the question we're going to chase, all the way down through the ice and into the black water below. Could a whole ocean of liquid water somehow be worse than having no ocean at all? Could it be worse, in a strange way, than the empty space around it? To find out, we have to start at the surface, and Europa's surface is unlike anything else in the solar system. It is smooth, bright, and covered in scars that look like a shattered eggshell wrapped around a moon. Those cracks are the first clue, and they are trying to tell us something about what moves beneath them. Look closely at Europa, and it seems someone took a white marble and cracked it 1,000 times. Its surface is covered in long, dark lines. They stretch for hundreds of miles, curving and crossing like veins, or like the shell of an egg that has been dropped and caught just before it fell apart. Some run reddish-brown against the bright white ice. From far away they look almost delicate. Up close, each one is a wound miles wide. That pattern is the first great clue, and it points to something moving underneath. Start with what Europa's surface is made of. It is water ice, frozen so cold and so hard that it behaves like rock. If you stood on it, it would feel like stone under your boots, not like a skating rink. The temperature there drops to around 260 degrees below 0 Fahrenheit. That is cold enough to shatter steel. Now here is the part that stunned scientists. Europa is smooth, shockingly smooth. If you shrank the whole moon down to the size of a bowling ball, it would be smoother than almost anything you could buy in a store. There are barely any tall mountains, and barely any deep craters. That smoothness is a mystery, because the solar system is a shooting gallery. For billions of years, rocks and comets have rained down on every world out there. Our own moon is scarred head to toe with craters, some ancient, most untouched for ages. Europa should look the same. Instead, its face is fresh. Something has been erasing the damage. Something keeps wiping the moon's surface clean and smooth, over and over, like a chalkboard being wiped between lessons. And whatever does the wiping has to come from below the ice. That is what the cracks are whispering. They are places where the crust has split, shifted, and healed. In some regions, the ice looks broken into chunks and refrozen, like a jigsaw puzzle that was smashed and then glued back together with the pieces slightly out of place. Scientists call these jumbled zones chaos terrain. They are the fingerprints of a restless, moving layer hidden underneath. For years, that raised a thrilling possibility. If the surface keeps breaking and refreezing, then maybe material from deep inside travels up to the top, and material from the top sinks back down. Maybe the ice is a doorway. Maybe whatever hides in the ocean below leaves traces on the surface where we can finally reach it. A doorway swings both ways, though, and the surface of Europa is a deadly place to stand, for reasons we will reach soon. What matters right now is simpler and stranger. Every crack, every jumbled patch, every smooth-healed scar points to the same conclusion. There is something warm and mobile beneath all that frozen stone. The obvious guess was liquid water. A hidden ocean, flexing and cracking the ice from below. It was a beautiful idea. It was also, for a long time, only a guess. Nobody had proof. You cannot see through miles of ice with a camera. So how do you prove an ocean exists when it is buried, invisible, and impossible to reach? The answer came from an unexpected place. It came from watching how Europa disturbs the invisible force field of the giant planet it orbits. Jupiter is a monster wrapped in an invisible cloak, and that cloak gave away Europa's deepest secret. The giant planet spins fast, and deep inside it churns a layer of metallic hydrogen, a strange form of matter squeezed so hard it conducts electricity. That churning turns Jupiter into a colossal magnet. It wraps the entire region in a magnetic field so vast and so powerful that it dwarfs anything around Earth. Europa orbits right inside it, swimming through Jupiter's magnetism like a fish through a current. In the late 1990s, a spacecraft named Galileo, after the same astronomer who first spotted the moon, swung past Europa again and again. On board was an instrument that measures magnetic fields, and it noticed something that should have been impossible. Europa had a magnetic field of its own, a weak one, a flickering one, and it pointed in a direction that kept changing, always seeming to push back against Jupiter's field, like a shadow that shifts as the light source moves. That was the giveaway. Here is the simple version. When you move a magnet near certain materials, you can create a second temporary magnetism inside them. Salt water is one of those materials. Salt water conducts electricity, and anything that conducts electricity will answer a moving magnetic field with a field of its own. It is the same basic trick that runs the electric motors in your home, just turned inside out. So the logic clicked into place like a key in a lock. Jupiter's field sweeps across Europa. Europa answers back with a field of its own. For that to happen, there has to be a thick, salty, electrically conductive layer hidden inside the moon. The only substance that fit the clues was a global shell of salt water, wrapped around Europa beneath its frozen crust. The measurement did more than hint. It pinned down that the conductive layer sat near the surface, and that it had to be big and salty. A buried ocean was the only answer that fit. After decades of guessing, scientists finally had their proof written in magnetism instead of light. Sit with the scale of that for a moment. We confirmed an entire ocean, one that may hold twice the water of Earth, without ever seeing a single drop of it. We never drilled, we never sent a probe into the water. We read the ocean in the way a moon nudged the magnetic breath of a planet as it passed. That is how clever and how desperate the search for life beyond Earth has become. Proof of an ocean only sharpened the real question, though. An ocean of water is one thing, an ocean of life is another. Earth's oceans are alive because they are fed, warmed, stirred, and lit in just the right ways. Take away any one of those, and even a vast sea can become a barren desert of water. So the story turns. We stop asking whether Europa has an ocean. we start asking what kind of ocean it is, how deep, how warm, how salty, whether anything down there could ever feed and breathe and grow. And the first shock is the sheer size of it. Because when scientists worked out how deep this hidden sea might go, the number they landed on made Earth's mightiest oceans look like puddles. Drop a stone into Earth's deepest ocean trench, and it would fall for almost 7 miles before touching the bottom. On Europa, that same stone might fall for 60 miles or more. That is the scale we're dealing with. Europa is a small moon, smaller than our own, yet the ocean it hides could be one of the largest bodies of liquid water anywhere near us. Scientists estimate the ice crust on top runs somewhere between 10 and 20 miles thick. Below that, the water may plunge down another 40, 50, even 60 miles before it reaches the rocky seafloor. Hold that picture for a moment. On Earth, the average ocean is only about 2.5 miles deep. Our seas are a thin, wet film smeared over a giant ball of rock. Europa flips that idea on its head. Its ocean is a deep, world-spanning layer, and the rock lies buried far beneath it. Add up all that water, and the totals are staggering. Europa's hidden sea may hold more than twice the water of every ocean on Earth put together. Take the Pacific, the largest ocean on our planet, deep enough to swallow the tallest mountains with room to spare. Now add the Atlantic, the Indian, the Arctic, every gulf, every bay, every trench, then double the whole thing. That is roughly what may be sloshing quietly inside a moon you could hide behind your hand. And it has probably been there a very long time, possibly for billions of years, longer than complex life has existed on Earth. A dark, patient, enormous ocean, sealed away and stirring in the black. For anyone hunting for life, this sounded almost too good. Water is the one ingredient every living thing on Earth depends on. We are mostly water ourselves, and here was a moon with an ocean so large it made our own planet look stingy by comparison. If sheer quantity of water were all that mattered, Europa would win in a landslide. This is where the dream starts to crack, quietly, from the inside. Because a bigger ocean is also a harder ocean to keep alive. Think about the challenge. The seafloor, where useful chemistry and heat might come from, sits at the very bottom. The ice crust, where fresh chemicals form, sits at the very top. And between them stretches an ocean so deep that getting anything to travel from one side to the other becomes a slow, uncertain journey. On Earth, our shallow seas mix easily. Sunlight reaches down into them. Storms churn them. Rivers pour nutrients in. Warm water rises. Cold water sinks. And the whole ocean turns over and stays fed. Europa lacks those same advantages. Its ocean is buried, dark, and possibly far too deep to mix from top to bottom. So the very thing that made Europa exciting, its immense volume of water, may also be part of the trap. A small, well-fed pond can teem with life. A vast, still-layered ocean might do something else entirely. It might separate into zones that never touch, where the top and the bottom become two different worlds that barely speak to each other. And to understand why a still-layered ocean is so dangerous, we first have to answer a simpler question. In a place this cold, this far from the sun, why is there any liquid water at all? Europa sits so far from the sun that sunlight arrives weak and thin, carrying barely a 25th of the warmth we feel on Earth. By every rule you would expect, its ocean should be frozen solid, top to bottom, a ball of ice with a rocky heart. Yet the water stays liquid. Something is heating it from within, and the source of that heat is one of the strangest engines in the solar system. The engine is Jupiter's gravity. Jupiter is enormous, more than 300 times the mass of Earth. When Europa swings close to it, that immense gravity pulls harder on the near side of the moon than on the far side. The whole moon stretches just slightly, like a rubber ball squeezed in a giant fist. Then Europa moves a little farther away in its orbit, the grip eases, and the moon relaxes back toward round. Squeeze, release, squeeze, release, over and over on every single orbit, forever. Now here is the trick that keeps the ocean warm. Anything you flex over and over gets hot. Bend a paperclip back and forth quickly and touch it to your lip, and you will feel it grow warm from the bending alone. Europa gets flexed by a force billions of times stronger, on a scale that spans an entire world. All that endless kneading generates heat deep inside the moon. Scientists call it tidal heating. It is friction, but on a planetary scale, and it may be enough to keep a global ocean from freezing. There is one more piece to the puzzle, and it is beautiful. Europa has help. It is locked in a gravitational dance with two neighbouring moons, Io on the inside and Ganymede on the outside. For every one lap Ganymede makes around Jupiter, Europa makes 2, and Io makes 4. This tidy rhythm is called a resonance, and it works like a group of children timing their pushes on a swing. Each moon tugs on the others at just the right moments, keeping their orbits slightly stretched and off-centre. That stretch is exactly what forces Europa to keep flexing. Without those neighbours, the squeezing would fade and the ocean might slowly ice over. So the picture that emerges is genuinely wonderful. A moon kept warm by gravity instead of sunlight. An ocean heated from below by the endless pull of a giant planet and the patient timing of its sister moons. Life, some scientists argued, could skip the sun entirely out here. It could feed on this inner heat instead, the way creatures on Earth's deep sea floor feed on heat leaking from our own planet. For a while, that idea seemed to seal the case: warmth, water, chemistry. What more could life want? Tidal heating hides a dark twist, though, and this is where the trouble begins to gather. The heat rises and falls over long stretches of time, and scientists now question whether enough of it reaches the rocky seafloor to do the work life may need. We will return to that seafloor later, because a chilling question waits down there. For now, notice something stranger. All this violence, all this flexing and hidden heat, stays completely invisible from space. From a distance, Europa looks like the calmest, most peaceful world you could imagine. A smooth, glowing pearl hanging in the dark. That calm is a mask, and what it hides may be the most hostile surface any traveller will ever face. From orbit, Europa is one of the most beautiful sights in the solar system. It glows. Its icy surface reflects sunlight so well that it shines like a polished pearl, bouncing back most of the light that hits it. Among all the moons and planets circling the sun, few are as bright. It looks pure, serene, almost gentle. That serenity is a lie, and it may be the most dangerous lie Europa tells. Step onto that shining surface, and the first thing that would strike you is the silence. Europa carries almost no air. Its atmosphere is so thin it barely deserves the name, a faint whisper of gas clinging to the ice, millions of times thinner than the air you're breathing right now. In a place with that little air, there is nothing to carry sound. You could scream and hear only the blood moving in your own ears. It is a silence deeper than any desert on Earth. Then there is the cold. The surface hovers near 260 degrees below zero, and at the poles it plunges even further, down toward 370 below. At those temperatures, the ice underfoot is harder than concrete, and any warmth in your body would begin bleeding away instantly. Europa would try to freeze you from the boots up. The stillness plays another trick on the eye. Europa has no weather in the way we know it, no drifting clouds, no rain, no changing seasons. The scene barely shifts from one day to the next, so the whole world seems frozen in time, a photograph rather than a place. Peaceful, empty, safe-looking. That is the trap. Because the deadliest thing about Europa's surface is completely invisible. Imagine standing there, looking up. Jupiter fills a huge slice of the sky, striped and swirling, so large it looks close enough to touch. It is a breathtaking view, and it is quietly killing you. Streaming out from that giant planet, unseen and silent, is a storm of energy so violent that no living thing from Earth could survive it in the open for long. You would feel calm, you would see beauty, you would sense no danger at all. And that is exactly why the surface of Europa is so deceptive. Every signal your senses send you would say this place is peaceful. Every signal would be wrong. On Earth, we learn to fear the things we can see. A cliff edge, a rising wave, a predator's eyes. Europa breaks that instinct. Its greatest threat gives off no light, no sound, no warning. It pours down constantly, day after day, soaking into the ice and everything on it, including any machine or explorer foolish enough to linger. Scientists have known about this danger for a long time, and it shapes every plan we make to study the moon. It is the reason we cannot simply park a spacecraft over Europa and stay. It is the reason landing there is a nightmare of engineering. This invisible storm rules the entire surface with an iron hand. So what exactly is pouring out of Jupiter? What is this silent force strong enough to kill an astronaut, fry a robot, and reshape the chemistry of an entire moon? To understand it, we have to look at the monster planet next door, and the deadly halo of radiation it wears like a crown. Jupiter wears a crown of radiation so violent it would kill a human standing on Europa in roughly a single day. To understand where it comes from, picture Jupiter's magnetic field, that invisible cloak we met earlier. It does more than reveal hidden oceans. It also works like a giant trap. It catches particles, tiny charged pieces of atoms, and it whips them around Jupiter at savage speeds, close to the speed of light. These particles pile up into vast belts of radiation, wrapped around the planet like glowing rings you cannot see, and Europa orbits right inside the worst of them. This is one of the harshest radiation environments in the entire solar system. The numbers are brutal. In roughly a single day on Europa's surface, an unshielded human would absorb a dose of radiation heavy enough to prove fatal. No wound, no fall. The invisible storm alone would be a death sentence. Machines fare little better. Radiation this intense tears through electronics, scrambling circuits and corrupting memory, frying the delicate brains of a spacecraft. Every hour spent bathing in it chips away at a robot's life. This single fact has haunted every mission scientists have ever tried to design for Europa. You cannot simply fly a probe there and let it orbit calmly overhead. The radiation would destroy it. That is why the spacecraft now on its way to Europa was built in such a strange manner, but we will come to that remarkable machine later. For now, focus on what this endless radiation does to the moon itself. It hammers the surface constantly, working like a relentless sandblaster made of energy instead of grit. When those speeding particles slam into the ice, they break water molecules apart, splitting them into pieces. They cook the surface chemistry, they darken the reddish stains in the cracks. In a very real sense, the top of Europa is being slowly chewed away and rearranged by Jupiter's fury, layer by layer, for as long as the moon has existed. Here is the strange part. This same brutal process might, in theory, help life rather than doom it. When radiation splits the water ice, it creates useful chemicals, including oxygen and other reactive molecules. On Earth, life runs on chemistry like that. Oxygen is fuel. So the radiation that makes the surface lethal could, in principle, be manufacturing ingredients that a living ocean would love to eat. For years, that idea gave scientists real hope. A poisoned surface feeding a living sea. A moon that turns a death ray into food. It was the kind of twist that makes the search for alien life so thrilling. Hope has a habit of shrinking when the measurements come in, though. And here, two hard questions were waiting. The first was about the ice itself. All that oxygen forms at the surface, yet the ocean that might use it lies far below. So how thick is the barrier between them? How solid is the seal separating the poisoned top from the sea underneath? For a long time, nobody truly knew. The answer would decide whether the surface could ever feed the deep. Then a spacecraft took a careful reading of the crust, and the result made scientists uneasy. Because the ice, it turned out, may be far thicker and far more sealed than the dream could afford. For decades, scientists argued over a single number that could decide whether Europa is alive. How thick is its ice? The debate split into two camps. One camp believed in a thin shell, maybe only a few miles of ice over the ocean. A thin shell would be wonderful for life. It would mean the ocean sits close to the surface, that cracks could reach all the way down, and that fresh chemicals from above could tumble into the water below. The other camp argued for a thick shell, tens of miles of solid ice, sealing the ocean away like a lid welded onto a jar. Everything hangs on which camp is right, and for years nobody could settle it. Cameras only see the surface. To measure the depth of the ice, you need to peer inside it. Then a spacecraft called Juno gave us a clue, and it was a clue nobody hoping for life wanted to hear. Juno carried an instrument that reads the faint microwave glow given off by the ice, a glow that changes depending on how deep and how solid the crust is. During a close pass over Europa, it took the measurement. The ice shell in the region it studied came out around 18 miles thick and possibly more. Some readings pushed the estimate even higher, toward the height of 4 Mount Everests stacked on top of one another. Sit with that comparison. To reach the ocean, you would have to drill down through a wall of ice taller than 4 of the tallest mountains on Earth, piled end to end. That is roughly 3 times deeper than humans have ever drilled into our own planet, and we would be doing it through frozen water in a killing radiation field hundreds of millions of miles from home. The thickness alone was discouraging, but Juno found something worse. Scientists had hoped the ice might be riddled with deep cracks and channels, open highways carrying chemicals from the surface down to the sea. Instead, the measurements suggested that the flaws in the ice were tiny and shallow, small pockets and fractures near the top far too weak and far too small to serve as real pathways to the ocean. Think about what that means. The poisoned, oxygen-rich surface and the hidden ocean may be separated by a barrier that is thick and nearly sealed, a lid with no keyhole. If the fresh chemicals made up top cannot travel down, then the ocean below is cut off from one of its most promising food supplies. This is the moment the dream started to curdle for many researchers. A thin, cracked shell meant an ocean connected to the outside world, fed and refreshed. A thick, sealed shell means an ocean that could be trapped in its own darkness, stewing in whatever chemistry it started with billions of years ago, with little coming in and little going out. It is the difference between a house with open windows and a house bricked up on every side. One breathes, the other slowly suffocates. Still, thickness is only part of the story, and even a sealed ocean might survive if it makes enough of its own food from within. So scientists turn to the next question. Forget for a moment whether the surface can feed the ocean. How much fuel does Europa actually produce in the first place? That question led straight to oxygen, the ingredient everyone was counting on. And the answer, when it finally arrived, was smaller than the dream could bear. Everyone expected Europa to be an oxygen factory. When the real measurement came in, the factory looked more like a trickle. Oxygen matters enormously in the search for life. On Earth, complex living things run on it. It is the fuel that powers our cells, the reason we breathe. So when scientists imagined life in Europa's ocean, they pictured oxygen made at the surface by all that radiation, then somehow feeding creatures in the deep. For a long time, their best guesses said the moon might produce a huge amount of it, enough to make the ocean richly breathable. Those guesses covered an enormous range. Some models said Europa might make only a few pounds of oxygen every second. Others said it could churn out more than 1,000 kilograms every second, a roaring torrent of the stuff. That is a giant gap, and nobody knew where in that range the truth actually sat. The whole question of whether the ocean could breathe hung on it. Then the Juno spacecraft flew close and for the first time sniffed the space around Europa directly. Its instruments counted the particles streaming off the moon as radiation split the surface ice apart. From those readings, scientists could finally calculate how much oxygen Europa really makes. The answer came out near the very bottom of the old predictions. About 12 kilograms of oxygen per second, roughly 26 pounds. Every second, Jupiter's radiation cracks the ice and frees about the weight of a large sack of dog food in oxygen, over and over, all across the moon. That still sounds like a lot, and in one sense it is. Added up, it comes to around 1,000 tons of oxygen a day, enough in theory to keep 1 million people breathing. But set against the soaring hopes of earlier models, it was a letdown. The moon sat at the stingy end of the scale, making far less than the dream required, and the lead scientist described the process with a haunting image. He called the ice shell a kind of lung for Europa. The moon breathes, in a sense, taking in radiation and exhaling oxygen from its frozen skin. But a lung is only useful if the breath reaches the body, and here the comparison turns cruel. Europa's lung sits on the outside, exposed to space, while the ocean that needs to breathe is buried far below. So the discovery cut 2 ways at once. It confirmed that Europa does make oxygen, which is good news. It also revealed that the supply is thinner than expected, narrowing the odds that the ocean holds enough fuel to support hungry complex life. A smaller lung, breathing onto a sealed lid. some scientists pointed out a sliver of hope. The moon might have breathed harder in the distant past, making more oxygen long ago, or the amount made today might still be just enough for simple, tough microbes, the kind that survive on almost nothing. Life on Earth can cling to astonishingly little, but every one of those hopeful ideas runs into the same wall we hit before. The oxygen is made up top, the ocean is down below, and between them stands miles of thick, nearly sealed ice. Which brings us to the cruelest question in the whole story. Even if Europa makes oxygen, and even if that oxygen is exactly what the ocean needs, is there any way for it to actually get down there? Or does it simply pile up on the surface, trapped forever above a sea that can never taste it? Making food is one thing, delivering it is another, and on Europa, delivery may be where the whole dream dies. Picture the setup. All the fresh oxygen forms at the surface where radiation splits the ice. The ocean that might use it sits below, under a crust of ice that Juno suggests is thick and nearly sealed. For the ocean to breathe, oxygen has to make a journey downward through all that frozen rock-hard water, and that journey is far harder than it sounds. There are only a few ways down, and each one has a problem. The first way is through cracks. If deep fractures split the ice from top to bottom, oxygen-rich material could slide down them into the sea. But the recent measurements suggest the cracks are shallow and small, healing over near the surface, rarely reaching the ocean far below. The highways scientists hoped for may be little more than dead ends. The second way is through the slow churning of the ice itself. Ice this thick can behave a little like extremely stiff, cold taffy. Over enormous spans of time it can creep and turn, carrying chunks of surface material downward. This process is called convection, and it might drag some oxygen along for the ride, but it is painfully slow, and it may only reach part of the way down before stalling. Whether it delivers a meaningful amount to the ocean is far from certain. The third way is through the chaos zones we met earlier, those jumbled regions where the surface seems to break apart and refreeze. If they truly connect to the ocean, they could act like occasional trapdoors, dumping surface chemistry into the deep. But scientists still argue about how often that happens, and how much actually gets through. Here is the uncomfortable truth that ties it all together. We know Europa makes oxygen. We have no idea whether more than a trace of it ever reaches the water. The moon could be sitting on a sealed jar, generating the perfect fuel on the lid while the contents inside starve. Compare it to a kitchen with a locked airtight pantry. The pantry might be stuffed with food, but if the door will not open, the family inside the house goes hungry all the same. It hardly matters how full the shelves are if nothing can get through the door. That is the shape of the fear. Europa may have water, warmth, and even a source of fuel, yet still fail to come alive, simply because the pieces cannot reach each other. A living world needs its ingredients in the same room. Europa may keep them in separate sealed compartments that almost never mix. And notice how strange this makes the moon. Empty space offers nothing, and it is honest about it. Europa offers everything a living ocean could want, then may quietly withhold the one thing that would let those gifts combine. It dangles the promise of life and then locks the door. Yet even this may not be the deepest problem. Suppose, against the odds, that oxygen does trickle down. Suppose the ocean gets fed from above. There would still be a second, older question waiting at the very bottom of the sea on the rocky floor where the water meets the stone. Because life may need more than food raining from the ceiling. It may need heat and chemistry rising from the floor, and whether Europa's seafloor can provide that has recently taken a dark turn. At the bottom of Europa's ocean, in total darkness, sits a rocky floor that could hold the key to everything. Or it could be the place where the last hope quietly dies. To see why the seafloor matters so much, look at the strangest ecosystems on our own planet. Miles down in Earth's oceans, far below where any sunlight reaches, there are cracks in the seafloor where hot, mineral-rich water gushes out of the rock. We call them hydrothermal vents, and around them, in pitch black, entire communities of life thrive. Giant tube worms taller than a person, ghostly crabs, clouds of bacteria. They feed on the chemistry pouring out of the vents, turning the energy in those hot fluids into food. Scientists call this trick chemosynthesis, life powered by chemicals instead of light. That discovery changed how we think about alien life. If creatures on Earth can live in cold, dark, crushing depths with no sunlight at all, then maybe Europa's dark ocean could do the same. All it would need is vents on its seafloor, leaking heat and chemistry into the water above. For years, that was the great backup plan. Even if the surface could not feed the ocean, the floor might. Vents do not appear by magic, though. To crack the seafloor and let hot fluids escape, you need the rock beneath the ocean to be squeezed, heated, and fractured. On Earth, our planet's inner heat and shifting plates do that work. On Europa, the job would fall to the same tidal flexing that keeps the ocean warm, that endless squeezing from Jupiter's gravity reaching all the way down to the rocky core. Here is where the trouble starts. Recently, scientists built careful computer models of Europa's rocky interior, trying to figure out whether Jupiter's pull actually flexes the rock hard enough to crack it, and the results were discouraging. In several of these studies, the forces tugging on the core came out too weak. The rock would bend a little, but never enough to fracture, never enough to open the pathways that hot fluids need to escape. If those models are right, Europa's seafloor might be quiet, sealed, a cold, unbroken floor with no vents feeding the dark water above. Think about what that would mean. The surface may be locked away by thick ice, and now the floor may be locked away too, unable to leak the heat and chemistry a hungry ocean would crave. Europa could be a sea pinched shut at both ends, cut off from the fresh surface above and the fiery rock below. It is like a sealed fish tank left in a closet. There is water inside, there might even be something living in it, but nobody ever opens the lid to drop in food, and no filter ever stirs in anything new. Slowly, quietly, the water goes stale, and whatever lives there runs out of whatever it needs. Scientists still argue about this. Some models leave room for vents, some point to signs of past activity. This question is far from settled, but the mere possibility of a Dead Sea floor knocked the wind out of one of Europa's best arguments for life, and it forces the hardest question of all. If the surface cannot feed the ocean, and the floor cannot feed it either, then where in all that dark water would a living thing ever find the energy to survive? At its deepest level, life is about flow. Every living thing you have ever seen survives by moving energy from one place to another. You eat food and breathe air, and inside your cells, one reacts with the other to release energy. Plants pull energy from sunlight. Vent creatures pull it from hot chemical fluids. In every case, life finds two things that want to react, and it stands in the middle, skimming off the energy as they combine. Scientists call this a chemical disequilibrium, a grand phrase for a simple idea. Life needs a battery, something charged, something out of balance that it can slowly discharge. Here is the quiet horror hiding in Europa's ocean. A battery only works if the two sides stay apart until you connect them. Let them touch and settle, and the charge drains away, and the battery goes flat. A flat battery cannot power anything, no matter how big it is. Europa's ocean may be a flat battery. Follow the logic we have built. On top, the surface makes oxygen, a powerful ingredient that living things love to react with. That is one side of the battery. On the bottom, the rocky floor could release fuels like hydrogen or sulfur compounds. The other side. Bring those two together in the water, and you would have exactly the kind of imbalance life feeds on. The oxygen from above meets the fuel from below, and in the middle, something could live off the reaction. Now remember the two blows we just landed. The thick sealed ice may block the oxygen from ever reaching the water. The quiet, unfractured seafloor may keep the fuel from ever rising into it. If both ends are truly shut, then the two halves of the battery never meet. The ocean has no charge to give. An ocean like that could sit there for billions of years, enormous and dark and utterly still, holding all the raw parts of a battery that will never connect. Water everywhere, and no spark anywhere. Picture two magnets in separate sealed rooms. Apart, they hold the potential to snap together with real force. Locked in different rooms, though, they do nothing at all. Their power is real and completely useless, because they can never reach each other. Europa's ocean may keep its oxygen and its fuel in exactly that kind of separation. This is what makes the moon so much crueler than empty space. Empty space has no battery to offer, and it never pretended to. Europa carries all the pieces of one, then may keep them forever unplugged. It is the difference between a poverty of nothing and a poverty of locked riches. One is simply barren, the other is a vault full of gold with no door, and the darkness makes it worse. On Earth, sunlight is a second battery, an endless flood of energy raining from the sky, powering nearly all life on the surface. Europa's ocean never sees a single ray of it. Whatever energy exists, there must come from within, from chemistry alone. If that chemistry stays locked and balanced, there is no backup waiting, no sunlight to save it. So we have followed the fear from the ice to the floor, and found a sea that may be starved from both directions. Yet even a starved ocean leaves traces, and one telescope managed to read a strange message written in the ice above. That message hints at what the water below is truly made of, and it points to something deeply out of balance. In 2023, the James Webb Space Telescope turned its golden eye toward Europa and read a chemical message frozen into the moon's skin. What it found was carbon dioxide, the same gas we breathe out, locked into the ice on Europa's surface. That alone was interesting. But the truly important part was where the carbon dioxide was sitting. It clustered in one particular region, a scarred, jumbled patch of terrain, rather than spreading evenly across the whole moon. That pattern was a clue about where the carbon came from. Scientists worked through the possibilities. The carbon dioxide could have been dumped on the surface by comets or meteorites. It could have been cooked up by radiation acting on other materials. Or it could have risen from the ocean below, carried up through the ice from the water hidden deep inside. When they studied the details, the comet and radiation explanations fell short. The best fit was the last one. The carbon was coming from inside Europa, from the ocean itself. That was a genuine thrill. For the first time, we had a hint of what the hidden sea is actually made of, read from millions of miles away. Europa's ocean contains carbon, one of the essential building blocks of every living thing we know. On paper, that is fantastic news. Life as we understand it is built on carbon. Then came the twist buried in the chemistry. The way the carbon appears, along with other clues, points to an ocean that is heavily oxidized. To understand what that means, think about what oxygen does to metal. Leave an iron nail out in the rain and it rusts. Oxygen attacks it, changes it, wears it down. Oxidizing chemistry is aggressive chemistry. It pulls things apart and locks them into new forms. A little of that can help life. Too much of it can wreck the delicate molecules life depends on. If Europa's ocean is flooded with oxidizing chemistry and starved of the gentler ingredients that balance it, the water could be a harsh place for anything trying to build the fragile structures of a living cell. The ocean might be closer to a slow, corrosive bath than a nurturing broth. Remember the oxygen we followed earlier, made at the surface by radiation. Some of it likely does sink into the ocean over immense spans of time, tilting the water toward that oxidized, rusting kind of chemistry. What may be missing is enough of the opposite, the fuels and reducers from a busy seafloor that would keep the whole system in balance. An ocean tipped too far one way is a chemical seesaw stuck hard on the ground. So the telescope handed us a gift wrapped around a warning. Yes, Europa's ocean holds carbon. Yes, it is chemically active. But it may be active in a lopsided, unfriendly way, tilted toward chemistry that tears molecules apart faster than life could ever build them. Every new fact keeps folding into the same shape. Europa has the ingredients. Europa keeps them locked or separated or out of balance. The moon looks generous and behaves like a trap. And there was one more thing the telescope went looking for, something that would have changed everything if it had been there. For years we thought we had caught Europa in the act of spraying its ocean into space, offering us a free sample with no drilling at all. The telescope hunted for those sprays. What it saw, or failed to see, deepened the mystery even further. For a few electric years it looked like Europa was handing us a gift. We thought the moon was spitting its ocean straight into space. The idea came from the Hubble Space Telescope. On a handful of occasions, starting around 2013, Hubble caught faint hints of something rising off Europa's surface. They looked like plumes, towering jets of water vapour blasting up through cracks in the ice, some possibly reaching 100 miles high or more. If real, they would be spectacular. They would also be the single most useful thing Europa could possibly do for us. Think about why. Drilling through miles of radioactive ice to reach the ocean is a nightmare we may never manage. A plume changes the game entirely. If the ocean is venting into space, then a spacecraft would only have to fly through the spray, open its instruments, and taste the water directly. No drilling, no landing, just a robot sailing through a fountain of alien ocean, sampling a hidden sea in a single pass. It would be the discovery of a lifetime. For years that hope glowed. The plumes seemed to promise a shortcut past every barrier we had run into, a natural pipeline connecting the buried ocean to the open sky. Whole missions were imagined around flying through them. Then the James Webb Space Telescope took a hard, careful look. Webb is far more sensitive than Hubble. If Europa were actively spraying water, methane, or other gases into space, this telescope was built to catch even faint traces of it. Scientists pointed it at the moon and searched, and they came up empty. No clear plume, no obvious jet of water vapour, no fresh spray of gases hanging above the surface. In the moment Webb looked, Europa appeared quiet and closed. That does not prove the plumes never happen. They could be rare, flickering on for a while, and then falling silent for years. Europa might have been between eruptions when Webb watched. The earlier Hubble hints might still turn out to be real, but the failure to confirm them landed as another quiet disappointment in a long line of them. Here is why it stings. Every plume would be a doorway between the ocean and space, a place where the sealed sea leaks out into the open. Lots of active plumes would suggest an ocean that connects easily to the surface, refreshed and exchanging material with the world outside. A moon with few or no plumes suggests the opposite, a sea locked away behind its ice with almost no leaks at all. The missing sprays fit the same grim picture we keep uncovering. Europa may be far more sealed, far more cut off than we hoped. It also robs us of the easy answer. With no reliable plumes to fly through, getting a real taste of Europa's ocean becomes brutally hard. We are left studying the moon from a distance, reading faint clues in the ice, guessing at the water below like doctors trying to diagnose a patient they are never allowed to touch. Yet the clues are still there. There is one special place on Europa where the ocean seems to have pushed its fingerprints all the way to the surface, a single scarred window into the deep. Scientists have stared at it harder than anywhere else on the moon, and what it shows us is both our best hope and a fresh reason to worry. There is one place on Europa that scientists return to again and again, a scarred region where the hidden ocean seems to reach up and leave its mark on the surface. They call it Terra Regio. It is a sprawling patch of chaos terrain, that jumbled, broken and refrozen kind of landscape we met earlier, stretching more than 1,000 miles across. Something has churned this region hard. The ice looks disrupted, shoved around, resurfaced far more recently than most of the moon. And packed into that torn-up ground, telescopes have found a remarkable collection of chemicals. This is where the carbon dioxide clustered most heavily. It is also where scientists spotted something even more homey: ordinary table salt. Sodium chloride, the very same salt that flavours your food and fills Earth's oceans, appears to be concentrated in Terra Regio, tinting the ice a faint yellowish colour. On Earth, salt in the sea comes from water flowing over rock, dissolving minerals and carrying them along. Finding that same salt here whispers that Europa's ocean has been in contact with rock, dissolving it, just like our own seas do. Put the clues together, and Terra Regio starts to look like a window. A place where material from the buried ocean has travelled up through the ice and painted the surface with the ocean's own chemistry, salt from the water, carbon from the water, all of it gathered in one torn, resurfaced scar. If we want to know what Europa's sea is made of without drilling into it, this battered patch of ground may be the closest thing to a free sample we will ever get. That is the hope. And it is a real one. Terra Regio tells us the ocean touches rock, carries salt, holds carbon. Those are exactly the sorts of things a living ocean might have. Look closer though, and the window comes with a warning etched into the glass. For starters, a window that opens in only one small region hints at how rare the exchange really is. If ocean material reached the surface freely, all over the moon, we would see its fingerprints everywhere. Instead, we see them concentrated in a few scarred spots, which fits the same story of a mostly sealed, mostly isolated sea that only rarely breaks through. And there is a nastier possibility. The chemicals we see in Terra Regio have been sitting on the surface, soaking in Jupiter's radiation. That radiation attacks and rearranges them, so even our best window may show us chemistry that has been scrambled and cooked since it arrived, a distorted reflection of the ocean rather than a clear one. We are reading a message that the surface has already smudged. Still, Terra Regio remains the single most promising place on Europa, the one spot where the moon seems to hand us pieces of its hidden heart. Every future mission will study it closely. Every instrument will strain to read it. Yet all of this dances around a deeper, older problem that no amount of chemistry can fix. Even if the water holds salt and carbon and the perfect balance of fuel, Europa's ocean suffers from one condition that has haunted the idea of complex life from the very start. It is drowned in permanent, total darkness. And darkness, it turns out, is its own kind of executioner. Imagine an ocean where the sun has never once touched the water, across 4 billion years of unbroken darkness. That is Europa. Above the ocean sits miles of ice, thick and solid. Below the ice, the water falls away into a blackness so complete it is hard to picture. Sunlight, even the weak sunlight this far out, cannot punch through miles of frozen crust. So every drop of Europa's ocean has spent its entire existence in perfect darkness. The deepest midnight and the brightest noon look exactly the same down there. Black. On Earth, that would be a death sentence for almost everything. Nearly all life on our planet traces back, one way or another, to sunlight. Plants and tiny ocean drifters capture light and turn it into food through photosynthesis, and then everything else eats them, or eats the things that ate them. Peel back the whole food web on Earth, and at the bottom you almost always find the sun. It is the great engine feeding the living world. Europa's ocean has that engine switched off permanently. Photosynthesis is simply impossible in water that never sees light. Whatever lives there, if anything does, could never rely on the trick that powers the vast majority of life on our world. It would be locked out of the single most productive source of energy life has ever found. That still leaves a crack of hope. We keep coming back to those deep-sea vent creatures on Earth that live in the dark on chemistry alone. Life can survive without light. But here is the crucial part. Those dark ecosystems on Earth are tiny compared to the sunlit world above them. They're rare, thin, scattered oases rather than lush jungles. Take away the sun, and even a living ocean can only support a faint, sparse whisper of life instead of a teeming abundance. So darkness sets a ceiling. Even in the best case, where Europa's ocean somehow gets fed and stays balanced, the total amount of life it could hold would likely be small. Thin colonies of microbes clinging to whatever energy they can scrape together. A quiet, meagre existence in an enormous black sea. The dream of glowing alien creatures drifting through Europa's depths runs straight into this wall. In a lightless ocean, there is nothing to power a rich, crowded world. Picture the difference between a rainforest and a single hardy weed growing in a cave. Both are alive. One bursts with colour and motion, and countless species fed by floods of sunlight, while the other barely hangs on in the gloom. Europa, at its most hopeful, is the weed in the cave. At its least hopeful, the cave is empty. The darkness carries a strange emotional weight too. This is an ocean the size of a world, older than complex life on Earth, that has never known a single sunrise. If something does live there, it lives blind, in silence, in cold, with no sky and no seasons and no light to mark the passing of unimaginable ages. It is one of the loneliest pictures in all of science. The darkness is fixed. It will never lift. But darkness is only one of the pressures bearing down on this ocean. There's another force pressing on the deep water, a physical one, growing stronger with every mile you descend, and at the very bottom it becomes something almost unimaginable. Sink down through Europa's ocean mile after mile, and the weight of all that water above you keeps building, until at the very bottom it presses down with a force that would crush a submarine like a paper cup. Pressure comes from a weight. The deeper you go in any ocean, the more water piles up overhead and the harder it squeezes. On Earth, the deepest point we know is the bottom of the Mariana Trench, almost 7 miles down. The pressure there is already staggering, more than 1,000 times the pressure you feel standing on a beach. Machines sent to that depth have to be built like armoured eggs just to keep from imploding. Now remember how deep Europa's ocean may run. Possibly 60 miles or more of water stacked from the underside of the ice all the way to the rocky floor. Europa's gravity is gentler than Earth's. only about 1/7 as strong, which softens the squeeze a little. Even so, pile up that much water, and the pressure at the very bottom of Europa's sea could rival or beat the crushing depths of the Mariana Trench. The floor of that alien ocean is one of the highest pressure places anywhere near us. Here is the reassuring part first. Pressure by itself does not necessarily kill life. Down in the Mariana Trench, in that bone-crushing dark, we still find living things. Strange fish, shrimp-like creatures, microbes. They evolved bodies that handle the squeeze because at those depths there is nothing to crush, no air pockets to collapse, just flesh and fluid pressed evenly on all sides. So a deep, high-pressure ocean can still, in principle, hold life. The trouble is what extreme pressure can do to water itself. Squeeze water hard enough, and it stops behaving the way you expect. At the enormous pressures found at the base of a very deep ocean, water can freeze into strange dense forms of ice, even while it stays warm. This is exotic heavy ice, packed so tight by sheer force that it behaves nothing like the fluffy ice of a winter pond. And if a layer of this dense ice forms along Europa's seafloor, it would build yet another wall, sit with that. The oxygen up top may be sealed out by the thick surface ice. The fuel at the bottom may be sealed in by quiet, unfractured rock. And now, at the deepest point, a floor of pressure-forged ice could slide between the water and the stone, adding a third barrier, blocking the ocean from touching the very rock that might feed it. It is like wrapping a locked box inside a second locked box inside a third. Each new seal makes it harder for the ingredients of life to ever find one another. Europa keeps stacking walls between the water and everything the water needs. So the picture sharpens with every layer we peel back. A moon that looks, from far away, like the most promising ocean world beyond Earth. Up close, a sea possibly capped by miles of ice, starved of surface chemistry, cut off from its own sea floor, and now perhaps floored with a crust of exotic ice as well, wall after wall after wall. We have been treating this ocean as ancient and steady, a patient sea waiting billions of years. But that raises a question we have quietly skipped. Has Europa's ocean truly held stable all that time? Or has it been shifting, changing, maybe even slowly freezing in ways that could matter enormously for anything trying to survive in it? We have been picturing Europa's ocean as timeless, a steady sea waiting patiently for billions of years. Nature rarely holds that still. Everything about Europa depends on a delicate balance. The ocean stays liquid because Jupiter's gravity keeps flexing the moon and generating heat. But that heat is not constant. It rises and falls as Europa's orbit shifts over long ages, nudged by the same neighbouring moons that drive the flexing in the first place. When the heat runs high, the ocean could grow and the ice could thin. When the heat runs low, the ocean could shrink and the ice could thicken, creeping downward from above. So the moon we see today may be only one frame in a very slow film. That idea carries a chilling possibility. Europa's ocean might be freezing. Not quickly by human standards, but over enormous spans of time. If the internal heat is fading, the ice above would keep growing thicker, pressing down, slowly stealing the liquid layer away. An ocean that was once close to the surface, cracked and connected, could be retreating deeper and sealing itself off as the ages pass. If that is happening, then the thick, isolated sea we have been describing is a snapshot of an ocean already partway through dying. Turn the idea around, and it gets stranger. Maybe the ocean is younger than we assume. Maybe it has thawed and frozen more than once, warming during high heat stretches and icing over during cold ones. A sea that keeps freezing and melting is a brutal home. Every time the ice advances, whatever chemistry was building in the water gets disrupted, scattered, or locked away. Life needs time and stability to take hold. An ocean that lurches between warm and frozen may never grant either. This is the problem of time, and it is easy to overlook. It is tempting to imagine habitability as a switch, on or off. In truth, it is more like a window that can open and close. A place might be perfect for a while, then slip out of the sweet spot as its heat, its chemistry, or its ice slowly change. Europa could have been more welcoming in the distant past, or it might become so far in the future, while the present moment finds it in a hostile, sealed phase. Think of it like a campfire. In the right window it gives steady warmth, and you can gather around it. Too early, and it is only cold wood. Too late, and it is dead ash. The fire is inviting for a limited time, and timing is everything. Europa's ocean may be a campfire, and we have no guarantee we are meeting it during the warm hours rather than the cold ashes at the end. And even if the timing is perfect, even if the ocean is warm and stable right now, one enormous problem still towers over all the others. It is a problem that would remain even if Europa had light, heat, balanced chemistry, and open pathways from top to bottom. Having all the parts of life is one thing. Assembling them into something alive is another entirely. And that step, the leap from lifeless chemistry to a living thing, is a mystery so deep that we have never fully cracked it, even here on Earth. Gather every ingredient for a cake on your counter, and you still do not have a cake. You have flour, eggs, sugar, and heat sitting there, doing nothing, until something combines them in exactly the right way. Life is the same, only far more mysterious. Even if Europa's ocean holds water, carbon, energy, and the right chemistry, none of that guarantees a single living thing. Somewhere between lifeless chemicals and the first living cell lies a step we barely understand. Scientists call the origin of life a biogenesis, the moment non-living matter first crosses over into life. And here is the humbling truth. We do not know how it happened, even on Earth. That is worth sitting with. Our own planet is covered in life, from the deepest rock to the highest cloud. Life clearly began here at least once, around 4 billion years ago. Yet despite all our science, nobody has fully explained the recipe. We know some of the ingredients, we can guess at some of the conditions, but the actual leap, the assembling of ordinary molecules into something that copies itself, grows and evolves, remains one of the greatest unsolved puzzles in all of science. If we cannot fully explain how life started on a warm, sunlit, endlessly varied planet like Earth, then think about the odds on Europa. There, the ocean is dark. The chemistry may be locked and lopsided. The energy may be faint and hard to reach. The very conditions that make it hard to feed life also make it hard to spark life in the first place. Building the first living thing may need rich, busy, constantly mixing chemistry, the kind a sealed, starved ocean struggles to provide. So Europa could be a kitchen stocked with ingredients where no cook ever arrives. The flour and eggs and sugar of life, water and carbon and energy, may all sit in the cold dark, never combining into anything that breathes. A world can hold every part of life and still remain utterly lifeless, simply because the parts never took the impossible step of coming alive. This is a different kind of emptiness, and a deeper one. Earlier we worried the ingredients might be sealed apart. Now we face the chance that even perfectly mixed, they might never ignite. Chemistry does not owe us life. It can sit balanced and inert forever, following its rules, never once crossing the line into something that wants to survive. Some scientists suspect that life, once the conditions are right, might start fairly easily. Others suspect it is fantastically rare, a fluke that may have happened only once in our entire solar system right here. If they are right, then even a warm, well-fed, perfectly balanced European ocean could be as barren as a sealed jar of clean water, full of promise, empty of life. We simply do not know which is true. That is the maddening heart of it. Europa sits at the crossroads of the biggest question we have ever asked, whether life is common or vanishingly rare, and it refuses to give us the answer from a distance. Which brings us to the strangest realization of this whole journey. A giant ocean of liquid water, warm and salted and ancient, might turn out to be one of the most disappointing places in the solar system, and that disappointment would say something almost unbearable about how alone we might be. To feel the full weight of it, compare Europa to the honest, empty dark that surrounds it. Empty space asks nothing of your hope. It is cold, black, and silent, and it never once pretends to be anything else. When you look into the void between the stars, you expect nothing, and the void delivers exactly that. There is an honesty to it, a clean, simple emptiness. Europa plays a crueler game. Europa arrives wrapped in everything a living world should have. A vast ocean, larger than all of Earth's seas combined. Liquid water, the very thing we search the galaxy to find. Warmth, generated by a giant planet's endless pull. Salt and carbon and a source of oxygen. From a distance, it checks nearly every box on our wish list for life. It looks like the answer to the loneliest question we have ever asked. Then, one by one, the boxes turn out to be traps. The water is real, but it may be sealed under miles of unbreakable ice. The oxygen is real, but it may never reach the sea that needs it. The seafloor is real, but it may be too quiet to feed anything. The chemistry is real, but it may be lopsided or locked or drowned in permanent dark. Even if every one of those problems somehow resolves, the spark of life itself may never catch. Europa offers the feast and then bolts every door to the dining room. That is why this moon can feel worse than empty space. Empty space is a poverty of nothing, and it is upfront about it. Europa is a poverty of locked riches, a treasure vault with the promise painted on the outside and the door welded shut. The void breaks no promises because it makes none. Europa makes every promise and may keep none of them. There is a special cruelty in that. Imagine wandering a desert, dying of thirst and finding a sealed glass tank the size of a lake, full of clear water you can see but never touch. The desert around you was always honest. It offered nothing, and you knew it. The tank is the torment, because it dangles everything you need just out of reach. Europa is that tank, hanging in the dark beside Jupiter, an ocean you can almost taste and possibly never drink. And here is the part that reaches past Europa itself. If a world this perfect on paper turns out to be dead, what does that say about all the other ocean worlds out there? Astronomers now believe hidden oceans may be common across the galaxy, tucked inside icy moons and distant worlds by the countless millions. If our nearest, most promising ocean is a sealed and sterile tease, then maybe most of those other oceans are too. Maybe the galaxy is full of water and starved of life. That thought should unsettle you. For decades, Europa carried our hope that Earth is not alone. A dead Europa would be more than one disappointing moon. It would be a hint that the universe might be far emptier of life than we ever wanted to believe, an ocean of oceans, and almost nothing swimming in any of them. Before we surrender to that gloom, though, there is a rival to consider. A smaller, humbler moon, far from Jupiter, that seems to be doing everything Europa cannot. And it makes Europa's silence sting all the more. Far beyond Jupiter, circling Saturn, there is a moon so small that its entire width is shorter than a drive across a single big state like Texas. Its name is Enceladus, and this tiny world may be showing up mighty Europa in the most humbling way possible. Enceladus is a fraction of Europa's size, a bright little ball of ice just over 300 miles across. Like Europa, it hides a saltwater ocean beneath its frozen shell. On paper it seems far less impressive, a lightweight next to Jupiter's grand ocean moon. Yet Enceladus does something Europa may not do at all. It sprays its ocean into space. At the south pole of Enceladus, giant cracks in the ice nicknamed the Tiger Stripes tear open, and out of them roar enormous geysers. Plumes of water vapor and ice grains blast hundreds of miles up into space, feeding a faint ring around Saturn. This moon is actively venting its hidden sea, flinging pieces of its ocean out into the open where anyone can catch them. And someone did. A spacecraft called Cassini flew straight through those plumes, again and again, sampling the spray directly. It tasted the ocean of Enceladus without ever landing or drilling. What it found was breathtaking. Salt, confirming a real sea in contact with rock. Organic molecules, the carbon-based building blocks that life uses. And signs of hydrogen, a chemical that hints at hot water reacting with rock deep below. The very kind of seafloor activity that could power life. Compare that to Europa. Europa may be sealed shut, its ocean locked away, its seafloor possibly quiet, its plumes missing or rare. Enceladus flings its ocean skyward, connects its deep water to space, and shows clear signs of the hot, active seafloor chemistry that Europa might lack. The little moon does, freely and openly, almost everything the giant moon may fail to do. Sit with how strange that is. For decades, Europa was the star, the celebrity of the search for alien oceans. Enceladus was an afterthought, a small icy moon nobody expected much from. Then Cassini flew through those geysers, and suddenly the underdog looked like the better bet. Size and fame counted for nothing. What mattered was whether the ocean could reach out and be sampled, whether its chemistry was alive and active. And on those tests the tiny moon shone. It is a lesson worth remembering. A big, promising ocean sealed behind walls may be worth less than a small ocean that opens its doors. Enceladus proves that a hidden sea can connect to the wider world and show us its secrets. Europa, so far, mostly proves how easily a promising world can lock us out. This contrast also sharpens the fear about Europa. We know an icy ocean moon can be generous, because Enceladus is. So when Europa stays silent, sealed and stubborn, that silence starts to look less like shyness and more like emptiness. The comparison strips away our excuses. Europa could be spraying, venting, sharing. It mostly is not. Still, we cannot convict Europa on hope alone, or on the good behaviour of a distant rival. To judge Europa fairly, we have to look harder at the water itself, at the exact stuff dissolved in that ocean. Because even if the sea were open and reachable, its chemistry might be hostile in ways we have only begun to suspect. And it starts with the salt. Salt gives life to Earth's oceans. In the wrong amounts, salt can also kill. We have already seen that Europa's surface carries ordinary table salt, the same sodium chloride in our seas, hinting that the ocean has touched rock and dissolved minerals. That was encouraging. But the full story of Europa's chemistry is messier, and parts of it are far less friendly. Start with how salty the ocean might be. Nobody knows the exact figure, and estimates range widely. Some models suggest Europa's sea could be far saltier than Earth's oceans, a heavy brine loaded with dissolved minerals. On Earth, life handles a certain saltiness with ease, but push the salt too high, and the water turns hostile. Extremely salty water pulls moisture out of living cells, drying them from the inside, the same way salt preserves meat by drawing the water out and leaving nothing for microbes to use. A sea salty enough could be a natural preservative, a place where the very chemistry that flavours it also strangles life. Then there is the kind of salt, which matters as much as the amount. On one side of Europa, the side that faces into Jupiter's radiation and catches material from the volcanic moon Io, the surface is stained with sulfur compounds. Radiation cooks these into sulfuric acid and sulfur-rich salts. If chemistry like that works its way into the ocean, or if the ocean already carries heavy loads of sulfur-based salts, the water could lean harsh and sour rather than gentle and life-friendly. Some models paint parts of Europa's chemistry as closer to battery acid than seawater. Here the picture splits, and the split matters enormously. If Europa's ocean is dominated by the friendly, Earth-like table salt we glimpsed at the surface, the odds for life look better. If instead it is a heavy, sulfur-soaked, acidic brine, the odds drop hard. And right now, from millions of miles away, we cannot tell which ocean we are dealing with. The same moon could be hiding a sea much like ours, or a sea that would dissolve a living cell on contact. This uncertainty is its own kind of torture. Europa keeps offering a hopeful clue, the sodium chloride, then undercutting it with a worrying one, the sulfur and acid. It refuses to settle into either a friendly world or a clearly dead one. It hovers in between, daring us to guess. Life on Earth does teach us to be careful before giving up. We have found microbes thriving in salt lakes so briny almost nothing else survives, and others living in acid pools that would burn human skin. Life is stubborn, and it colonizes places that look impossible. So even a harsh, salty, acidic European ocean might still, in some corner, host something tough enough to endure. But endurance is a low bar. There is a vast gap between a few hardy microbes clinging to survival in a hostile brine and a rich, thriving ocean of life. Even in the hopeful case, Europa's chemistry may permit only the barest, most stubborn flicker of living things, scraping by in a sea that seems designed to wear them down. The salt is only one variable, though. Woven through it is another that could tip the whole ocean toward life or toward death. A hidden number we have almost no way to measure from here. It decides whether the water is a cradle or a corrosive bath, and it may be the single most important thing about Europa's ocean that we simply do not know. There is a single hidden number that could decide whether Europa's ocean is a cradle or a graveyard. That number is its acidity. Chemists measure acidity on a scale called pH. Low numbers mean acidic, like lemon juice or vinegar, or the acid in a car battery. High numbers mean the opposite, alkaline, like bleach or ammonia. In the middle sits neutral water, and near the middle sits the comfortable range where most life on Earth thrives. Stray too far in either direction, and the chemistry turns violent. Strong acids and strong bases both tear apart the delicate molecules that living things are built from. Earth's oceans sit in a gentle, life-friendly range, and they have stayed there for a very long time. That steadiness is a quiet gift. It gave life a stable chemical home to grow up in. Europa's ocean may have no such gift, because we have almost no idea where its acidity falls. The problem is that everything feeding into Europa's ocean pushes it in uncertain directions. The oxidized, rusting chemistry from the surface could shove it one way. The minerals dissolving off the rocky seafloor could shove it another. Sulfur and radiation-cooked compounds could sour it further. Depending on how these forces balance, Europa's sea could sit anywhere from mild and welcoming to savagely acidic. And a savagely acidic ocean, the size of a world, would be one of the most hostile environments imaginable. Here is why this matters so much. Life cares about acidity for more than comfort. The wrong pH can shred proteins, unravel the molecules that carry genetic information, and prevent the delicate structures of a cell from ever holding together. In water that is too acidic or too harsh, the building blocks of life fall apart faster than they can assemble. It becomes almost impossible to go from scattered chemicals to a living thing, and hard even to keep an existing living thing intact. Think of it like trying to build a sandcastle in the wrong conditions. In damp, gentle sand, your castle holds its shape. In dry, blowing sand, every wall collapses as fast as you raise it. Life is that sandcastle, and pH helps decide whether the sand cooperates or crumbles. An ocean with the wrong acidity is blowing sand endlessly, everywhere, forever. And the cruelest part is how blind we are. We can measure Europa's acidity from Earth in no direct way at all. We can only build models, feed in our guesses about the chemistry, and watch the answers scatter across a huge range. Some models land in the friendly zone, others land in the corrosive one. The truth is locked inside the ocean, under miles of ice, waiting. So we arrive at a strange and frustrating place. We have chased Europa's ocean from its surface to its floor, through its ice and its oxygen and its salt, and again we hit the same wall. The most important facts, the ones that decide life or death, are exactly the ones we cannot measure from a distance. Europa guards its deepest secrets well. That helplessness has a root, and it comes down to one fierce, unresolved argument that has divided scientists for years. It is a fight over a single feature of the moon, a feature that changes everything else. Get it right, and the whole picture snaps into focus. Get it wrong, and every guess about Europa's ocean falls apart. The fight is over the ice. One question about Europa has split scientists into warring camps for decades. How thick is the ice? And they still have not agreed. We touched this fight earlier, but its true weight is worth facing head-on, because almost everything else hangs from it. The thickness of Europa's ice shell is the master switch. Flip it one way, and Europa looks alive with possibility. Flip it the other, and Europa looks like a sealed tomb. Very few questions in all of planetary science carry so much weight on a single number. Picture the two camps. On one side stand the thin ice believers. They argue the shell might be only a few miles deep, thin enough that cracks could reach the ocean, thin enough that surface chemistry could tumble down and feed the sea. In their Europa, the ocean and the surface stay in conversation, trading material, keeping the water fresh. It is a hopeful moon. On the other side stand the thick ice believers. They argue the shell runs tens of miles deep, a massive frozen lid sealing the ocean away from everything above. In their Europa, the sea is cut off, isolated, left to stew alone. It is a lonely moon, and possibly a dead one. Same moon, same data, much of the time. Opposite conclusions. The reason the fight endures is that the clues are maddeningly hard to read. A crack on the surface could form over a thin shell or a thick one. A patch of chaos terrain could mean the ocean is close, or it could mean warm ice is slowly churning far above the water. Even careful measurements from spacecraft have only sampled small regions, leaving open the chance that the ice is thin in some places and thick in others, varying across the moon like the crust of a planet with mountains and plains. This is what makes Europa so agonizing. The single fact that would settle nearly every argument, the true thickness and structure of that ice, keeps slipping through our fingers. Telescopes can study the surface. Distant flybys can grab a glimpse, but a glimpse leaves room for two entire opposing pictures of the same world, hopeful and hopeless both still standing, and the stakes could hardly be higher. If the thin ice camp is right, then much of the gloom we have been building starts to lift. Surface oxygen could reach the ocean, fresh chemistry could flow, the sea could be fed and balanced after all. But if the thick ice camp is right, then the sealed, starved, lonely ocean we have feared becomes the likely truth, and Europa slides toward that cruel category of a water world with everything and nothing at once. For years, scientists fought this out with models and arguments and scraps of old data, and the fight refused to end. It became clear that no amount of squinting from afar would ever settle it. The moon simply guards the answer too well. To truly know the thickness of the ice, and to finally measure the sea beneath it, we would have to go there and stay, circling the moon again and again, staring straight through the ice with the right eyes. And that is exactly what humanity decided to do. But sending anything to Europa means solving one of the hardest problems in all of space exploration. Before we meet the daring machine now racing toward that ice, we have to understand why almost every earlier attempt to truly know Europa fell short. Everything we think we know about Europa rests on a shockingly thin stack of real visits. For all the moon's fame, only a handful of spacecraft have ever gone anywhere near it, and none of them were built to study it properly. Our best close-up look came from a spacecraft named Galileo, which explored the Jupiter system through the 1990s and into the early 2000s. It gave us most of what we know, including the first strong evidence for the hidden ocean. It was a triumph. It was also, by modern standards, half-blind. Early in its mission, Galileo suffered a crippling failure. Its main antenna, the big dish meant to beam data home, refused to open properly. Stuck and useless, it forced the spacecraft to send its findings through a tiny backup antenna instead, at a painfully slow trickle. Imagine trying to send thousands of detailed photographs through a straw. The spacecraft had to ration every image, every measurement, choosing a precious few and abandoning the rest. Vast amounts of possible science were simply never sent. Because of that, Galileo mapped only a sliver of Europa at high detail. Most of the moon we have never seen up close at all. Whole regions remain blurry guesses. The stunning images we treasure, the cracked ice, the chaos terrain, the reddish scars, come from a scattering of close passes, not a full survey. We have been building our entire picture of Europa from a few sharp glimpses and a lot of shadow. Sit with that. One of the most studied, most dreamed about worlds in the solar system has been examined in real detail across only a fraction of its surface by a wounded spacecraft decades ago. Everything else is inference, modelling, and hope. When scientists argue about the ice, the ocean, the chemistry, they are arguing over a puzzle with most of the pieces still missing. Later missions helped, but always in passing. Spacecraft bound for other targets stole quick looks at Europa as they flew by. A probe studying Jupiter itself swung close enough to grab a few precious readings. Powerful telescopes, near Earth and in space, squinted at the distant moon and teased out hints of its chemistry. Each added a brushstroke. None gave us the full portrait. Europa has never once had a spacecraft dedicated entirely to understanding it. That is the strange gap at the centre of this whole story. We have spent decades calling Europa our best hope for alien life, writing books about it, imagining creatures in its seas. And yet, until very recently, no one had ever sent a mission built from the ground up to answer the questions that matter. We fell in love with a world we had barely met. That gap comes down to something simpler and harsher. Europa is brutally hard to reach and study. The distance is enormous. The radiation is lethal. The ice is thick. Every instinct an engineer has about how to explore a world runs into a wall at Europa, where the environment fights back against the very machines we would send. To finally crack the moon's secrets, scientists had to design something new, something tougher and cleverer than anything sent before. a spacecraft able to survive a place that destroys spacecraft. Understanding why it had to be so extreme means understanding just how hostile Europa truly is to any visitor, living or mechanical. The obvious way to study a hidden ocean is to drill down and scoop out the water. On Europa, that obvious plan borders on impossible. Start with the ice. We have seen it may be miles thick, perhaps as tall as several stacked mountains of frozen water. On Earth, our deepest drills have clawed only a few miles into solid rock, and those projects took years, huge machines, and enormous crews standing right beside the hole. Now move that job to a frozen moon hundreds of millions of miles away, with no crew, no resupply, and no way to fix anything that breaks. A drill would have to melt or grind its way down through miles of rock-hard ice, alone, in the dark for months or years, with everything depending on it never once jamming. The engineering challenges pile up fast. A melting probe would need a powerful, long-lasting heat source to keep boring downward. It would need to send its findings back up through miles of refreezing ice above it, a signal fighting its way to the surface. It would have to avoid getting stuck as the melted water froze solid again behind it, sealing it into the very ice it was crossing. Each of these problems alone is fearsome. Together they push at the edge of what we can currently build. Even landing on Europa at all is a nightmare. The surface may be jagged in ways we cannot fully see from orbit, studded with sharp ridges and shattered ice that could tip or tear a lander apart. Picking a safe spot to touch down on a world we have barely mapped is a gamble, and whatever machine we land has to survive that invisible storm of radiation pouring from Jupiter, which chews through electronics and shortens the life of anything exposed. That radiation is the quiet villain behind every plan. It means a lander cannot simply sit on Europa for years patiently drilling, because the radiation would kill its circuits long before the drill reached the ocean. It means a spacecraft cannot linger in a close orbit, slowly gathering data, because the same storm would fry it. Time on Europa is poisoned. The longer a machine stays, the faster it dies. So the dream of a submarine gliding through Europa's ocean, or a drill punching straight down to the water, remains far in the future. The pieces are being studied, and someday such a mission may come. For now, though, the ice is too deep, the radiation too fierce, the distance too vast, the risks too high. Drilling into Europa's sea belongs, at present, to the realm of things we can imagine far more easily than we can do. Faced with all these walls, scientists made a clever choice. If you cannot safely stay near Europa, then do not stay. If you cannot drill into the ocean, then find another way to read it. Instead of one fragile machine sitting in the killing radiation, why not a tougher spacecraft that darts in, grabs its data in a quick close pass, and races back out to safety before the radiation can do its worst? That single idea reshaped everything. It is the reason the spacecraft now on its way to Europa looks and behaves so strangely. It was built to survive, designed around a single ruthless goal, to dart in, gather the truth, and get out alive. And it may be the most radiation-hardened robot humanity has ever flung across the solar system. Meet Europa Clipper, the armoured giant built to do the impossible. In the autumn of 2024, it rose off a launch pad in Florida and began the long hunt for the truth about Europa's ocean. Everything about this spacecraft is shaped by a single enemy: radiation. Jupiter's invisible storm would destroy an ordinary probe in weeks, so the engineers built Clipper to fight back, and the result is one of the strangest and toughest machines we have ever sent into space. At its heart sits a thick metal vault, a strong box with walls of dense metal wrapped around the spacecraft's most delicate electronics, its brain, and its memory. The vault soaks up the worst of the radiation, shielding the sensitive parts inside like a lead apron protects you at the dentist. Without that armoured box, the storm would scramble Clipper's mind within a few close passes. With it, the spacecraft can endure the punishment long enough to do its work. Clipper is also enormous. It is the largest spacecraft NASA has ever built for a mission to another planet. Stretch out its solar wings, the huge panels it uses to gather faint sunlight so far from the sun, and they span more than 100 feet, wider than a basketball court. It needs panels that big because sunlight at Jupiter is many times weaker than at Earth, and Clipper has to squeeze every drop of energy from that thin light to stay alive and powered. Then comes the cleverest trick of all. and it is about where Clipper chooses to fly. You might expect a spacecraft studying Europa to orbit Europa. Clipper does something smarter. It orbits Jupiter instead, on a wide, looping path, and only swings in close to Europa for brief, daring flybys before racing back out again. The reason is that terrible radiation, fiercest right around Europa. By spending most of its time farther out, and only dipping in for quick passes, Clipper limits how much radiation it absorbs, stretching its life across many visits rather than burning out in a few. The plan calls for dozens of these close encounters, around 50 flybys in all, each one skimming over a different part of the Moon. Little by little, pass after pass, Clipper will stitch together the detailed map of Europa that no earlier mission could manage. Where Galileo saw slivers, Clipper aims to see the whole. To do that, it carries a full suite of instruments, 9 of them, each designed to answer a different piece of the puzzle. Cameras to map the surface in sharp detail. Tools to read the chemistry of the ice and the thin atmosphere. Devices to probe the magnetic signs of the ocean. And an instrument built to peer down through the ice itself, hunting for the boundary where frozen crust gives way to hidden sea. This is the machine humanity built to end decades of guessing. It survives where other spacecraft would die, and it looks harder and longer and closer than anything before it. Every armoured panel and shielded circuit exist for one purpose: to keep Clipper alive in the storm long enough to read Europa's secrets. Yet before it can read a single one, Clipper faces a journey almost too vast to picture. Europa is nowhere near next door. To reach it, this spacecraft must cross a gulf so enormous and follow a path so strange and winding that the trip itself is one of the boldest voyages we have ever attempted. Europa is so far away that even travelling in a straight line at incredible speed, a spacecraft would need years to reach it. And Europa Clipper is not travelling in a straight line. The raw distance is hard to hold in your head. To reach Jupiter, Clipper must cross about 1.8 billion miles of space. Written out, that is a number with too many zeros to feel real. Picture it this way instead. Light itself, the fastest thing in the universe, takes around 3/4 of an hour to travel from Jupiter to Earth. Clipper, moving far slower than light, needs years to cross that same gulf. Here is the twist that makes the journey stranger. Clipper cannot simply point at Jupiter and fire its engines the whole way. It does not carry nearly enough fuel for that. Instead, it plays a kind of cosmic pinball, using the gravity of planets to fling itself forward for free. The trick is called a gravity assist. When a spacecraft swings close to a planet, it can steal a tiny bit of that planet's motion, whipping around it and flying away faster than it arrived, like a skateboarder grabbing the back of a moving truck for a boost. The planet barely notices. The spacecraft gains a huge kick of speed without burning a drop of extra fuel, so Clipper's path loops through the inner solar system before it ever heads for Jupiter. After launch, it swung inward toward Mars, using the red planet's gravity to bend and speed its course. Then it curved back toward home, aiming for a close pass by Earth itself, borrowing another boost from the very world it started on. Each flyby reshapes the path, adds speed, and slings the spacecraft a little closer to its distant target. The route looks less like an arrow and more like a long curving detour, a scenic road taken because the direct highway costs too much fuel to drive. All of this careful looping means patience. Clipper launched in the autumn of 2024, yet it will not arrive at Jupiter until the spring of 2030. Nearly 6 years in transit, 6 years of coasting through the dark, checking its instruments, adjusting its course, creeping toward a moon it was born to study. The scientists who launched it will wait more than half a decade just to begin the real work. And even arriving is only the start. Once Clipper reaches Jupiter, it must settle into its long looping orbit and begin the slow campaign of flybys, gathering Europa's secrets a little at a time across years of close passes. The mission is a marathon layered on top of an odyssey. Launch, cruise, arrive, then work, all stretched across a span of time long enough for a child today to grow well into their teens before the fullest answers come home. That is the price of Europa. It sits so far guarded by so much radiation that reaching it demands a spacecraft armoured like a tank, a route bent through multiple planets, and the patience to wait the better part of a decade. Humanity committed to all of it, spent the money, built the machine, and threw it across the solar system, all to answer one haunting question about a distant sea. Which raises the obvious wonder, when Clipper finally arrives and opens its eyes, what exactly will it look for? How does a spacecraft that cannot land or drill hope to read the truth of an ocean buried under miles of ice? Europa Clipper cannot touch the ocean, so it will read it the way a detective reads a locked room, by studying every clue that leaks out through the walls. Its most striking tool is a kind of radar that can see through ice. The spacecraft will beam radio waves down into Europa's frozen shell. Most bounce back from the surface, but some pierce deep into the ice before reflecting off whatever lies below. By timing those echoes, scientists can measure how thick the ice truly is, and maybe spot the exact boundary where solid crust gives way to liquid sea. This single instrument could finally end the thin ice versus thick ice war that has raged for decades. It is like tapping on a wall and listening for the hollow spot that reveals a hidden room. Then there are the magnetic tools. We learned earlier that Europa's ocean gives itself away by disturbing Jupiter's magnetic field. Clipper will measure that disturbance with far more precision than any mission before it. From the exact way Europa answers Jupiter's magnetism, scientists can estimate how deep the ocean is and how salty its water might be. The spacecraft will read the sea's size and saltiness without ever dipping a single instrument into it, purely by studying invisible magnetism. Clipper will also taste the moon in a way. Tiny particles constantly drift off Europa's surface, kicked up by radiation and micrometeorite strikes, forming a faint haze around the moon. As Clipper flies through that haze, special instruments will catch those particles and analyze what they are made of, sniffing the chemistry of the surface and any material that rose from the ocean below. If even a whisper of a plume exists, Clipper is built to fly through it and read its contents on the spot. On top of that, the spacecraft carries cameras and chemical sensors to map Europa in stunning detail. They will photograph the cracks and chaos zones, chart the temperature of the ice, and identify the salts and compounds scattered across the surface, especially in scarred regions where ocean material seems to reach the top. Every pass will add sharp new detail to a moon we have only ever seen in fragments. Put all these tools together, and a picture emerges of how Clipper hunts. It will not find life directly. That is important to understand. Clipper carries no net to scoop up alien fish, and no microscope to spot swimming cells. Its job is quieter and more foundational. It will judge whether Europa is habitable, whether the ocean has the right ingredients, the right chemistry, and the right connections to support life at all. It measures the stage, not the actors. That distinction matters enormously. Even in the best case, Clipper will come home with an answer about possibility, not proof. It might tell us that Europa's ocean is warm, salted, chemically balanced, and connected to a lively seafloor, a place where life could thrive. Or it might tell us the ocean is sealed, starved, and hostile, a place where life almost certainly cannot. Either answer would be historic. Neither would show us a creature. Still, judging the stage is exactly what we need right now. For decades we have argued in the dark, guessing at Europa from scraps. Clipper will finally replace guesses with measurements, and its very journey has already begun to shift the mood among the scientists who have waited their whole careers for this moment. Right now, as you take this in, a spacecraft the size of a basketball court is coasting silently through the dark, millions of miles from Earth, on its way to settle the greatest question about Europa. Europa Clipper is already out there, and it has years left to fly. Since it launched, the mission has been quietly hitting its marks. In its first months, Clipper stretched out its giant solar wings and instrument booms, unfolding into its full, strange shape far from any help. It aimed its cameras at distant stars to check that its eyes worked. Then it swung past Mars, using the red planet's gravity to bend its path and pick up speed, one of the slingshots that will carry it across the solar system. Next, it turns back toward home. In the closing weeks of 2026, Clipper is set to swoop past Earth itself, stealing one more gravity boost from the planet that built it, before flinging outward toward Jupiter for good. After that, the long, lonely cruise begins in earnest. A slow fall through the dark that will not end until the spring of 2030. Here is the quiet drama unfolding while Clipper flies. Back on Earth, the mood around Europa has been shifting, and not in the direction anyone hoped. In the years since the spacecraft launched, discovery after discovery has landed on the discouraging side. Readings suggesting the ice may be thick and sealed, measurements hinting the oxygen supply is thinner than dreamed, a powerful telescope failing to catch the plumes we counted on, models warning the seafloor might be too quiet to feed anything. One by one, the easy hopes have been chipped away, even as the machine meant to test them races through space. So Clipper is flying toward a colder question than the one it launched with. When it left Earth, many imagined it might confirm a warm, connected, living ocean. Now, with the mood tempered by hard results, more scientists brace for the other answer, that Europa's sea may be sealed, starved, and lonely after all. The spacecraft has not changed. Our expectations have. This raises the stakes rather than lowering them. Precisely because the recent clues lean grim, we need Clipper to replace fear and guesswork with real measurement. Only it can look through the ice and tell us at last whether the gloom is justified, or whether Europa has been hiding a warmer secret all along. The wait is its own kind of suspense. For the rest of this decade, Europa Clipper will keep coasting, then arrive, then begin its patient years of flybys. The people who will finally read its clearest answers may look quite different, older and greyer than the ones who cheered its launch. The truth about Europa's ocean is coming. It is simply taking its time crossing the void to reach us, and that leaves us right now suspended in the most uncomfortable position of all. We have built the case that Europa's ocean might be worse than empty space. We have a machine on the way to find out, but we do not yet know the verdict, so it is worth asking what each possible answer would truly mean, starting with the darkest one. What if Clipper arrives, looks through the ice, and finds a sea that is utterly, absolutely dead? Suppose the worst. Clipper arrives, peers through the ice, and finds exactly what we have feared. A vast ocean, warm and salted and ancient and utterly without life. What would that mean for us? At first, it would feel like a simple disappointment. Decades of hope, a beloved moon, and in the end, just cold water in the dark. But the meaning runs far deeper than one letdown, because of what Europa represents. Europa is close. It is nearby, reachable, and about as promising as an ocean world can look from the outside. It has everything on the checklist. If a world this well suited for life, right in our own solar system, turns out to be dead, then a heavy question follows us home. If not here, where? Astronomers now believe that hidden oceans may be scattered across the galaxy in staggering numbers, tucked inside icy moons and frozen worlds far from any sun. For years that idea fueled optimism. So many oceans, surely some must be alive. But a dead Europa would flip that hope on its head. It would suggest that having an ocean, even a big, warm, salty one, is not nearly enough. That water is common and life is not. That the galaxy could be soaked in seas and still be silent. This connects to one of the deepest debates in all of science. Some thinkers argue that life, given water and time, springs up readily wherever it can, and that the universe should be teeming with it. Others argue the opposite, that the leap from chemistry to life is so rare, so improbable, that it may have happened only a handful of times, or even once, in the whole vast cosmos. A dead Europa would hand a heavy point to the second camp. It would whisper that Earth may be something far more precious and far more alone than we assumed, rather than one lucky world among many. Sit with how strange that feeling would be. We would be surrounded by water, oceans beyond counting, and yet more isolated than ever. Every one of those seas would be a reminder that the ingredients of life are everywhere, and the spark almost nowhere. The universe would look less like a garden waiting to bloom, and more like an endless desert dotted with locked wells. And there is a quieter, more personal weight to it. For a long time, Europa has been a symbol of cosmic company, proof that we might share the solar system with something alive, even if only microbes in a dark sea. To lose that would be to lose a certain comfort. It would make the night sky feel emptier, and our own crowded, noisy living planet feel rarer and more fragile than we usually let ourselves believe, a dead Europa would not end the search for life. We would keep looking at other moons, other worlds, other stars, but it would change the tone of that search, sobering it, reminding us how easily a perfect-looking world can come up empty. It would teach us that hope alone proves nothing, and that the universe owes us no company. That is the darker path. Yet there is another possibility waiting behind the ice, and in its own way it may be even more unsettling than a dead sea, because if something truly does stir in that black water, then we would face a discovery so enormous and so dangerous that we may not be ready for it. Now, suppose the opposite. Clipper, or some mission after it, finds that Europa's ocean is alive. Even a single kind of microbe drifting in that dark water would be one of the most staggering discoveries in human history, and it would open a door we may not be ready to walk through. Start with the wonder, because it is real and enormous. Life on Europa would mean life began twice in one solar system, once on Earth and once on a moon of Jupiter, independently. That would change everything. It would tell us that life is something the universe does again and again wherever the conditions allow, rather than a fluke unique to our planet. In a single stroke, the galaxy would transform from a probably empty place into a probably crowded one. We would no longer wonder whether we are alone. We would know we never were. Tangled up with that wonder, though, is a serious danger, and scientists take it seriously. It is the problem of contamination, and it cuts both ways. The first risk is us contaminating Europa. Our spacecraft are built on Earth, and Earth is drenched in microbes. Despite careful cleaning, a probe can carry hardy bacteria across space. If a machine crashed into Europa, and those Earth microbes reached the ocean, they might survive, spread and overrun a fragile alien ecosystem before we ever got to study it. We could wipe out the very thing we came to find, or muddy the water so badly we could never tell what was native and what we brought. That is why missions like Clipper are planned so carefully, and why a spacecraft may be deliberately crashed away from Europa at the end of its life, rather than risk falling onto that fragile ocean. The second risk runs the other way, and it stirs older fears. What if something from Europa reached Earth? If a future mission ever scooped up Europan water and carried it home, scientists would have to handle it like the most dangerous substance imaginable, sealed away under the tightest containment we can build. An alien microbe, evolved in total isolation, could behave in ways nothing on Earth is prepared for. The odds of real harm are debated, and many experts think the danger is small. But the caution is deadly serious, because the cost of being wrong could be beyond repair. There is a heavier weight here too, one that goes past safety. If Europa holds life, then it becomes a world with inhabitants, however small, rather than a mere target to study. That raises questions we have barely begun to face. Do we have the right to drill into a living alien ocean? To risk disturbing it, sampling it, changing it? For the first time, we would have to weigh our hunger to explore against the possibility that we are trespassing on someone else's home, even if that someone is only a smear of microbes in the dark. So both answers carry a shadow. A dead Europa would leave us lonelier than before. A living Europa would hand us a discovery so profound and so delicate that we would have to grow up quickly to deserve it. Wonder on one side, danger on the other, and a moon that refuses for now to tell us which we face. Everything in the end comes back to that stubborn, silent ocean and to the question we still cannot answer. We have travelled all the way down, through miles of ice, across a killing storm of radiation, into the black water of a sea larger than all of Earth's oceans, and we arrive at the honest truth. We still do not know. That is the strange and humbling place Europa leaves us. After decades of study, after telescopes and flybys and brilliant minds, the moon guards its deepest secret as tightly as ever. Somewhere beneath that frozen shell lies an ocean that is either one of the most exciting places in the universe or one of the most heartbreaking. And it will not tell us which. Look back at everything we uncovered. An ocean confirmed by the way it bends a planet's magnetism. Water enough to drown Earth twice over. Warmth wrung from the endless pull of Jupiter, and then, clue by clue, the shadows gathering. Ice perhaps too thick to crack. Oxygen perhaps too trapped to reach the deep. A seafloor perhaps too quiet to feed anything. Chemistry perhaps too harsh, too salty, too sour, a darkness that never lifts, and a spark of life that may never catch. Add it all together, and Europa becomes the ultimate riddle. It holds every ingredient we associate with life, and may withhold every one of them at the moment it matters. That is what makes it feel, at times, worse than the empty space around it. The void promises nothing and keeps its word. Europa promises everything, and may turn out to be a sealed and silent tomb, a perfect ocean with no one home. But notice the word that keeps returning. Perhaps. Every dark possibility we raised is exactly that, a possibility, not a proven fact. The ice may be thinner than the gloomiest models say. The cracks may run deeper. The seafloor may glow with hidden vents we have not yet detected. The chemistry may sit against the odds in the narrow band that life can use. For every reason to despair, a door remains open, just a crack, letting in a thin blade of a light. That is why a spacecraft is crossing the dark right now, armoured against the storm, aimed at the truth. Within a few years, Europa Clipper will settle into its long loop around Jupiter and begin staring through the ice, again and again, until the guessing finally ends. One way or another, this generation will learn what lies beneath that frozen shell. We will replace perhaps with an answer, and whatever that answer turns out to be, it will change how we see ourselves. A dead Europa would teach us that oceans are cheap and life is rare, that our warm, crowded planet is more of a miracle than we ever admit. A living Europa would teach us that we share the cosmos, that life ignites wherever it can, and that we were never truly alone. Both answers are enormous. Both are waiting, right now, under miles of ice on a moon you can spot through a backyard telescope. So the next time you look up and find Jupiter, a bright, steady point in the evening sky, remember what rides beside it. A frozen moon holding a secret ocean, and inside that ocean, one of the biggest answers humanity has ever chased. We do not have it yet, but for the first time in history, we have reached out to take it, and soon, at last, that silent sea will have to speak.